Kind of like not all of our double displacement reactions form to precipitate or a water or a gas, not all of our redox processes are going to proceed as they're written. Luckily, we have a trusty and easy to handle tool called the activity series that we can consult to determine if a reaction is predicted to proceed as written. Let's start this conversation by reviewing the reactions that we saw in the last subsection. Each of these reactions is predicted to proceed as written. In all of these cases, the reactant element is more likely to exist as an ion than the reactant ions are. Now, the chemists would say that all of these elements, indicated with the orange arrows, are more reactive than the elements indicated with the green arrows. In this case, reactivity is defined as preference for forming ions. If we pair reactants for which this story isn't true, our reaction won't proceed. So, how do we decide whether we have a true story or fiction? Well, we use the activity series to help us do just this. The elements that are near the top of this series are more likely to exist as ions than the species towards the bottom of the series. In redox speak, the elements at the top are more likely to be oxidized. Lithium is your most reactive metal and will transfer electrons to nearly any reducible sample you mix it with. Platinum and gold, on the other hand, are very slow to oxidize and react with very little. Good thing, since a lot of our jewelry is made out of these two metals. Now, usually when we design a redox reaction, we're going to try to put some space between reactant pairs so that we know a reaction can occur based on the placement of the activity series. But even things relatively close together on the table can have very different behaviors. For instance, there's only one element between silver and platinum. Most platinum jewelry will exist untarnished for a long time, whereas silver needs to be polished to remove the black oxidation fairly frequently. There are quite a few ways to use this series to predict reactivity. You could just be given a list of metals and asked which is the most reactive. In that case, you would simply find all of the metals on your list and choose the one that's closest to the top. For this list, barium would win. Maybe you're asked which out of the same list is the most likely to be reduced. Since the species at the top are the most likely to be oxidized, it should make some sense that the species at the bottom are least likely to be oxidized. If they're least likely to be oxidized, then they're most likely to be reduced. So the answer to the second one would be palladium. I could ask you to determine which species might be able to form H2 if reacted with steam. Here, I've given you compounds instead of elements, but in all three cases, the cation is related to a metal that's part of the series. So look up those metals. You'll notice that the elements in the series are grouped by box colors, and each of those colors have a descriptor on the left-hand side of the image. In addition to determining whether two metals can transfer electrons between each other, this series can be used to determine if a metal will transfer electrons with water, steam, or an acid. Only the most reactive of our species will transfer electrons with water. Non-reactive metals will not transfer electrons with any of them. Of this list, only the calcium chloride is reactive enough to react with steam to form H2. But the bulk of what you'll be asked to do with this table is to determine if the story that you're given in balanced equation form is truth or fiction. So we'll start with a familiar one. This balanced equation, as written, claims that the sodium metal is more reactive than the silver cation. Sodium cations and silver metal couldn't be formed otherwise. Now, let's confirm that the story is true. Our job is to find both the reactant metal, sodium, and the reactant ion, silver, on the activity series. The sodium is found near the top with the flirts with everybody that walks by category. This means that it is, in fact, reactive and will prefer to be ions at the end of the day over being a reactive metal. So my table confirms that my balanced equation is true. But you didn't actually explain how, you say. I know. How do you not give me the benefit of the doubt yet? Keep in mind that you have to read your equation as it is written. But if the reactant metal is higher on the series than the reactant ion, your reaction will proceed as it is written. This means that your metal is likely to react and to form a compound. So this equation is a true story. Sometimes your equation won't be a true story though. So this equation as written, says that gold is reactive enough that it would prefer to be an ion over the silver cation. Now, if we consult the activity series and look up the metals, we see that silver is the more reactive of these two because it's higher on the series. More reactive means more likely to be an ion when compared with gold, which is the state that the silver is in on the reactant side of the reaction before anything happens. So there's no driving force for the reaction to occur in this case because everything's happy enough being what it is right now, relatively speaking. So this balanced equation is a false statement, and this reaction will not occur as written.